Across the globe, we're facing this massive, growing shortage of workers in STEM fields. It's a real crisis, right? It totally limits our ability to innovate and compete. But what if the secret to fixing this shortage has literally been hiding in plain sight, right inside our own minds? Welcome to The Explainer. Today, we're unpacking a really fascinating book chapter by David Uttal and Cohen. They argue that spatial thinking is actually the hidden cognitive key to unlocking STEM success. So let's jump right in and see how our brains construct the physical world.
Here is the roadmap for our cognitive mystery today. We're going to cover 1. STEM and spatial thinking. 2. Career prediction. 3. The expertise paradox. 4. Expert thinking. 5. The novice's struggle. And finally, 6. The power of training.
All right, let's kick things off with Section 1, STEM and Spatial Thinking, the cognitive key.
Before we go any further, we really need to pin down what we mean here. The chapter focuses heavily on spatial visualization. Basically, that's the cognitive process of apprehending, encoding, and mentally manipulating 3D forms. Think of it like the ability to hold a complex object in your mind's eye and just rotate it around to see the back. Or imagining what a 3D object would look like if you sliced it right down the middle.
And this example perfectly illustrates why that skill is so absolutely crucial. Picture the geological folds in the Canadian Rockies. Structural geologists have to look at those static rock formations and mentally undo millions of years of physical tectonic forces that smash the layers together. It's an intensely spatial and temporal puzzle. You literally cannot do this job without visualizing transformations across space and time.
Let's switch gears to chemistry and see how this builds. We have this concept called chirality, which is really just a fancy scientific way of saying handedness. Just like your left and right hands have the exact same parts, but you can't perfectly superimpose them on top of each other, molecules can actually have the exact same atoms, but totally different spatial layouts. And wow, this matters immensely in the real world. Back in the 1960s, the drug thalidomide was prescribed for morning sickness. One spatial version of that molecule cured the sickness, but its exact mirror image, its chemical twin, caused devastating birth defects. Same atoms, different spatial arrangement, wildly different consequences.
Right, which brings us to Section 2, Career Prediction, Predicting STEM Success.
So how do these foundational cognitive skills actually map onto real-world career trajectories? Well, the authors outline this absolutely massive data set to answer that. We are talking about 50 years of research following over 400,000 students in the Project Talent dataset. The findings? Honestly, they're staggering. High spatial skills strongly predict who will end up in math, engineering, and the physical sciences. On the flip side, lower relative spatial skills predict entry into fields like business, law, and medicine. But here's the crazy part. Spatial ability adds a unique predictive value entirely on its own. Even when you factor out how good someone is at math or verbal reasoning, spatial ability remains a completely independent indicator of STEM success.
If you map this out visually, you can really see the relationship. You've got math scores, you've got verbal scores. But then there's this massive added vector representing spatial ability. When you look at careers like engineering, math, and the sciences, the vector for spatial ability shoots way out. That length represents the massive value-added predictive power of spatial skills. Basically, if you want to know who's going to be an engineer, you absolutely have to know their spatial score.
But just as everything seems perfectly straightforward, we hit Section 3, the expertise paradox, a cognitive twist. And it poses a pretty massive question for us. If spatial skills are so critically important for entering STEM, why don't STEM experts actually use them? It is a huge plot twist in this whole cognitive mystery. So, the crucial point is captured perfectly in a 2011 bedrock mapping study by Hambrick and colleagues. They had geologists map underlying rock structures in a real-world task. When you look at the experts with high geological knowledge, their performance is basically a flat line. Whether their raw spatial ability was low or high, their accuracy was essentially identical. But for the novices, having high spatial ability made a massive difference. The experts somehow completely bypassed the need for raw spatial visualization.
Which brings us to Section 4, Expert Thinking, Bypassing Spatial Limits.
How exactly are they bypassing this? Well, the authors call it the circumvention of limits hypothesis. When a novice looks at a problem, they have to rely on grueling, time-consuming mental rotation and decontextualized spatial visualization. They're literally turning shapes over in their mind. Experts, on the other hand, rely on domain-specific semantic knowledge. They've built up this massive library of perceptual chunks. They bypass the spatial limits because they don't need to rotate the shape. They've already seen a variation of it 1,000 times.
The book chapter uses a brilliant analogy here. Think of a chess grandmaster. When they look at a chessboard, they aren't memorizing the exact spatial coordinates of 32 isolated wooden pieces. No way. They see abstract patterns, relationships, higher-order themes. They see patterns of attack and defensive structures. They rely on the meaning of the board. STEM experts do the exact same thing in their respective fields.
And we can actually measure this in the lab. In chemistry, when novices are asked to identify rotated 3D molecules, they show a classic mental rotation curve. The more the molecule is rotated, the longer it takes them to figure it out. But for experts, their reaction times are totally flat. They bypass the mental rotation entirely and just know the answer thanks to that vast semantic memory.
Let's move to Section 5, the novice's struggle. A brutal catch-22.
Because beginners don't have that vast library of expert knowledge yet, they are stuck. As the authors put it, novices face a catch-22. They lack the knowledge to succeed despite low spatial skills, but they can't get that knowledge without passing those spatially demanding early classes. To survive early STEM, you desperately need raw spatial skills. If you don't have them, you fail and you drop out before you can ever build the expert knowledge that would have eventually made those spatial skills unnecessary.
And the casualty rate of this catch-22 is devastating. 40%. Over 40% of college students who start in STEM either drop out entirely or switch to non-STEM majors. The data shows the breaking point usually hits right around their third semester. These aren't students who couldn't have become brilliant scientists. They're just students whose spatial skills weren't quite high enough to get them past that initial gateway.
Which leads us to our final and definitely most optimistic section, the power of training, upgrading the mind. The summary of this book chapter ultimately points to a powerful evidence-based solution. Spatial skills are not fixed at birth. They're highly malleable and they respond beautifully to practice. For example, Sorby and Bartmans created a targeted 10-week spatial training course for engineering students that yielded massive gains in retention. And broad meta-analyses confirm that when we train these skills, the effects actually endure over time, and they transfer to completely new, untrained tasks. We can literally upgrade a student's cognitive toolkit.
So, I'm going to leave you with this final thought. If we know spatial skills act as the gatekeeper to STEM, and we know these skills can be reliably trained, how many more scientific breakthroughs are we missing out on simply because we aren't teaching them? How much untapped genius is just sitting there? It is absolutely time to rethink how we train the scientists of tomorrow.